This lesson on hyperbolas is going to be very similar to what you saw for ellipses. The equations are going to look very similar. However, you're going to notice the differences in the sign and what we're really looking for to determine if our hyperbola is going to open left and right or up and down. So whether it will be horizontal or vertical. So when we are looking at the definition of a hyperbola, it's the set of all points for which the difference of the distances to the two foci is a constant. So for instance, you see in this picture we have a point at xy over here on this branch. So hyperbolas have two branches, and if we were to measure the distance from this point over to this focus point and to this focus point, notice those focus points are inside the curves, just like they were inside the ellipse, and a focus point for a parabola was inside the curve of the parabola. Same thing is going on here. But if you measured those distances and took the difference of them, it's always going to be the same value, no matter what point you're on. If you're here at a vertex or over here, or even over on this branch, if you were to measure the distance between that point and the two foci, it would always be the constant. So again, I want to remind you to be looking at how your equations and graphs and definitions of the different conic sections are, how they're similar and how they're different. So this hyperbolas don't have a major or minor axis like the ellipse did. It has a transverse axis. So it's not an axis of symmetry, nor is it a directrix line like it was for a parabola. It's called a transverse axis, and there's only one of them. And if your branches are opening horizontally, left and right, you will have a horizontal line for the transverse axis. If it was vertical, you would have a vertical line for the transverse axis. And these 2 points you're going to notice in our next picture, these are where only these 2 points are allowed to be called the vertex points or vertices. Okay, so here's another picture, and again, we're going to let A equal this distance from the center over to the two vertices. And C is still the distance from the center over to a focus point. So it would also be the same distance over here. Okay, now hyperbolas have asymptote lines, okay? And you're going to discover how to create them, how to draw them in, and how to determine the equation of those lines. So here's a picture of a vertical hyperbola where you notice the branches are opening up and down. These asymptote lines are really cool because they allow us to draw the branches within the asymptote lines. Remember, asymptote lines are lines where your graph is going to approach them but never really reach them. So they're guidelines for you when you're drawing in these branches. And again, notice these are going to be the vertex points, and the two focus points are along this transverse axis. Okay, so the one equation that you need to memorize for hyperbolas is this: c squared equals a squared plus b squared. When it was an ellipse, it was c squared equals a squared minus b squared, and a represented the distance that was the longer, it was the larger number, wasn't it? For an ellipse, we could determine if it was horizontal or vertical based on where that larger denominator was in the equation. So we cared about the larger number in a subtraction problem, correct? We don't care about a larger number if we're adding numbers together, do we? So for hyperbolas, we don't care about the larger number. That's not what determines whether it's going to be horizontal or vertical. It's going to be which one comes first in our equation. So this is the formula you need to memorize. I would highlight that on your notes. And again, going back up to the other picture above that you have on your notes for the horizontal and vertical hyperbolas, I would just notate that those are called the branches. Each one of those are called the branches that I was referring to. Okay, so again, on your side notes, I would write this down. We do not care about the larger number in the equation. That's not what we're going to look for in hyperbolas. We're going to look to see which one is coming first, because notice your equations. your equations have a minus sign in them. They're still equal to 1, so they look very similar to what the equation looked like for an ellipse. Ellipse had x minus h squared over some number squared plus y minus k squared over some number squared equals 1. Well, hyperbolas have a minus sign. So the positive quantity is what we're looking for. So for an ellipse, x squared always came first, and we just looked for the larger denominator. But for hyperbolas, we could have an x squared first or a y squared first. If you're looking on your first page of notes, you'll see that in your, right here. Look at these equations. Here, x squared is first, the y squared was negative. See the minus sign in here? Here, x squared was negative. So whatever one comes first, that will determine whether our branches are opening left and right or up and down. So in this box here, I want you to just, let's just draw a little picture. This doesn't have to be perfect here. The center, again, is going to be HK. HK was the vertex of a parabola. It was the center of a circle. It was the center of an ellipse. It's also the center of a hyperbola. So if we have horizontal branches, we'll have a horizontal line for the transverse axis. And just give yourself some distance A and some distance B. And then make those go out in both directions. So if you have a distance A here, you have a distance A here. I didn't really mean for this to be a actual box like a square. It could be a rectangle also. You could give it a different length for B or A, because again, we don't care about the bigger number. We don't care about the longer distance here. Not for hyperbolas. That was for an ellipse. So if you go in both directions, a distance of B and a distance of A, and then draw those in. This is going to be what I'm calling the box. And then when you use a ruler and you line this up, your asymptote lines, they are lines, and they're going through the corners of this box and through the center. And that is going to allow us to stay within the lines to draw our branches. So each one of these points right here would be the vertex points. And you're going to see how easy it is to figure these out, what you're going to do for this distance of the box. So somewhere over here, we would use our formula. We would calculate. Remember, you're going to take the positive root of c squared to get c, and they will be somewhere inside the branches, but along this transverse axis, just like the focus points were also along the major axis for an ellipse. So the same idea here. So we are going to determine the linear equations from those lines, and that is going to be some information I'm going to request of you guys. So over here, let's just draw a picture of what it might look like if we had, again, going out in both directions from the center of distance of A and a distance of B, and that would create our, what I'm calling the box. Our asymptote lines would go through those corners and through the center, and this would have vertical branches going through the vertex and kind of along the box, but staying within the asymptote lines. And then somewhere along here, we would have our focus points according to whatever this equation was, and taking the positive root of that. So again, it would have two equations. So you can come back to these notes. You could pause the video actually and write this down if you desire to have this all written out for yourself for your notes. But I'm going to jump to the next slide where we're going to get into the heart of this matter here, and just start off by just recognizing if it would be horizontal or vertical and where the center would be. So again, you could pause this to write all these down on that first page of notes. If you still have space, you should, in your Cornell sidebar. So in example 1, again, we are not looking for the bigger number here. This is not an ellipse. What is coming first, x or y? X is first, it's positive, so this is going to be a horizontal. It would have branches going out left and right. And again, I would advise you to sketch these out, just a little sketch on the side before you actually graph them, but we're not graphing these. And the center here would be 0, 0 because we have nothing with the x and nothing with the y. It would be like x minus 0 in parentheses and y minus 0 in parentheses, which we don't really need. So in this case, you should look at this and identify that y is first, so it's going to be a vertical hyperbola. The branches would open up and down. And you should, again, I want to caution you to be careful identifying the center. Remember, anything with y is k, and it's talking about the y coordinate. Anything in parentheses with x is talking about, it's the h. It's referring to the x coordinate. So what would make this 0? Opposite. -2. What would make this 0? Opposite. So it's +1. So your center would be -2, 1. So be careful identifying your center, just like you had to be very careful when it was a parabola. So now we're going to graph these. So in this case, you should look at that, and again, you can write down little notes on the side, like what comes first. If x squared comes first, it's horizontal. If y squared comes first, it's vertical. Where's the center? HK. Be careful of that. You can even draw a little sketch. In this one, x is coming first, so it's going to be horizontal. The center is going to be at 0, 0, so we would plot that and dash in your little transverse axis. It's not an asymptote line. This is a transverse axis. Its equation right here is at y = 0. Excuse me. Now, this part that I'm about to show right here, this is the same thing we did for an ellipse. Whatever number is under x squared, this is some number squared, and this is some number squared. And by the way, a referred to the larger number for an ellipse, but in hyperbolas, it's whether it's horizontal or vertical is determined by what comes first. But regardless of that, if you looked back at your equations, they're always letting this first number represent a, and this represents b. Because remember, our formula, c squared equals a squared plus b squared, we don't care about the larger number, right? So they're always just going to let this refer to some number squared. They're calling this a, and they're calling this b. So regardless of this, whether it's horizontal or vertical, we are going to go from the center left and right 2 units, and we're going to go up and down 5 units. The only difference now is that these 2 points, when we're going left and right 2, they're the only 2 points that we're calling the vertices, and you can go ahead and identify their coordinates. Just like we did for an ellipse, we're going to go up and down here 5 units and down 5 units, but they're not called co-vertices. Okay, these values just help you to sketch out this distance of what that box was I was referring to. So we're still going to go up and down and left and right from our vertex according to these the square root of these numbers that are over here. But only 2 of those points are called the vertices, depending on what kind of hyperbola we have. The other 2 just help us to create the box, and then we're going to use our ruler and go through the center and the corners of our box, and those are how we get our asymptote lines. And these asymptote lines help us to graph in our branches of the hyperbola. So your hyperbola branch should not go inside the box. It can get really close and kind of go alongside it, but it should be going through the vertex and then staying within the asymptote lines. So you have to have 2 of those branches, and now our picture is not complete until we have our 2 focus points, and we can identify what the value of C is to get them, and we can go ahead and identify their coordinates, and then we're going to go and find the equation of those asymptote lines. So for right now, we're going to use our formula, and so if C squared is 29, then C is the square root of 29. And as I mentioned last time, I'm now allowing you to use a calculator to estimate it. You could also leave it in reduced radical form and go out from your center point in that fashion, but we're using, probably most of you are using your calculator at this point. And so because the foci are going to be on a horizontal axis, we're going to subtract this value from the center point. We're going left and right from the center, which was 0, 0 in this case. Okay? So that is how we're going to get our coordinates. So 0 minus this value gives us this point, and 0 plus this value, because only the x values are changing for the focus points. This is horizontal. The y coordinates are staying the same as the y coordinate of what our center was. Okay, so we have that in reduced radical form. There's our 2 focus points. They're located there. And next we're going to go find the asymptote lines, but I'm running out of time on this video, so I'm going to stop this one and then go to part 2 to pick it up from there.